Hi everyone. In this video, we'll begin our discussion of differentiation, which will continue over the next several videos. So to begin today, we will look at the definition of the derivative and a few of the early consequences that fall out of that definition. So to begin, let's start with the definition of the derivative. So let f be a function from some subset d of the real numbers into the real numbers. And suppose that A is an element of the domain and is an accumulation point of D. Then the derivative of f at A is defined by the following limit definition. And in fact, we've listed two equivalent limit definitions here, both of which are commonly used. So we have f prime of A is equal to the limit as x approaches A of f of x minus f of A over x minus A, which is also equivalent to the limit as h goes to 0 of f of a plus h minus f of a over h, if those limits exist. When that limit exists, when f prime of a exists, then f is said to be differentiable at the point A. So let's first look at a few different elements of this definition. So the first thing I want to remark on is that here we are requiring both that A is an element of the domain and that A is an accumulation point of the domain. So, right, we have seen before that just because something is, you could in general think about some set D. If you took D to be the set here, 0 is an accumulation point of this set, but is not in this set. So if you took the function f from D, this set D into the reals defined by f of x is equal to x, you cannot talk about the derivative of this function at 0 because 0 is not in the domain. It is an accumulation point of the domain, but it's not in the domain. Likewise, if you were to take, for example, and change this set D to say simply be this set, okay? Again, this is a perfectly well-defined function. And let's say you wanted to talk about the derivative at 2, okay? Well, 2 is in your set, but every point of this set is an isolated point. So 2 is not an accumulation point, so you can't talk about the derivative. So again, you need both. You need the point to be in your domain and to be an accumulation point of your domain in order to talk about the derivative. So you could, for example, talk about the derivative if your domain was, so back to this example, but let's say we unioned on the point 0. Now 0 is in your domain and it is an accumulation point of your domain. So you could actually talk about the derivative of this function. So that's the first thing we want to know. Now, again, the reason those are important is now when we look at that limit definition, right, we see, first of all, just like right here, right, and over here as well, right, I need A to be in my domain in order for f of A to make sense, right? So certainly A has to be in my domain. I need A to be an accumulation point of the domain so that these limits, right, when I go to talk about these limits, I want these to be well defined. So this is why I need this to be an accumulation point, right? So again, both of those criteria are necessary to make sure that we can at least we can even make sense of talking about these particular limits in the context of taking the derivative. All right. Now, beyond that, like if you look at this, this is exactly the same limit expression we had back in chapter 1 when we talked about the derivative, and that you may have seen in an earlier real analysis course, right? So this is the, or even in a calculus course, right? You likely encountered this limit definition of the derivative. So many of sort of the structures of our proofs aren't going to change from ones you may have previously seen. The only things that are going to potentially change are I mean, you have to be a little careful about, exactly what we're talking about in terms of what points we can take derivatives at, what hypotheses we need of theorems. And we have to be a little careful there. So today we're going to see really these are going to be theorems you've seen before, either in a calculus course or maybe you prove them in an undergraduate real analysis course. But we're just going to take some slightly finer care of some of these details to make sure we're proving things as rigorously as possible. As we move on, we will start to look at new theorems that you are unlikely to have seen before, or maybe they were mentioned but not sort of fully written out. So we'll talk about those as we go. So we're both going to revisit some familiar theorems in more careful detail, while also expanding our depth of knowledge a bit by examining some new theorems. So before we do that, I want to start by just looking at two motivating examples. And these are two functions that we've looked at before in this course. So over here on the left, I have f of x is x times sine of 1 over x when x is not equal to 0, and 0 when x is equal to 0. Over here, I have g of x, which is almost identical to f of x, but I just have an extra factor of x here, right? So this is x squared sine of 1 over x when x is not equal to 0, and 0 again when x is equal to 0. So in the context we've seen them before, we've previously noted that if I look at here, for example, the limit as x goes to 0 of f of x. Okay, that will end up being, so this is going to 0. This is oscillating quite rapidly as we get close to 0. However, it's bounded between -1 and 1. So I have something going to 0 times something that's bounded. That's going to go to 0, which, by the way, is f of 0. Okay, so in particular, right, we have here that f is continuous at 0. Similarly, over here for g of x, right, we have that the limit as x approaches 0 of g of x will, for identical reasons, be 0, which is equal to g of 0. And so again, g is continuous at x is equal to 0. So then we want to sort of ask, okay, well, what more can we say now in the context of differentiation? So let's see. Well, we've said something about continuity. In fact, both of these functions are continuous for all real numbers. So they're continuous on their entire domain, which is all real numbers. Let's focus at 0 though, right? That's sort of the interesting point. And let's look at a limit definition of the derivative here. So let's see what we can say about differentiability. So the first thing to note, right back to my previous point. So 0, if I want to talk about the derivative at 0, I need the 0 to be in the domain. It is. And I need 0 to be an accumulation point of the domain. Well, it is, because the domain here is all real numbers. Okay, so I can at least try to make sense of this limit as x approaches 0 of f of x minus f of 0 over x minus 0. Now, if I plug in values here, substitute in values. So f of x, again, I'm really thinking here about what's happening when x is not 0, right? So x is approaching 0, but not equal to 0. So I'm going to just sort of deal with the case where x is not 0. So that would be f of x would be x times sine of 1 over x minus f of 0 is 0 over x minus 0. Okay, so I just have some zeros here. This will be the limit as x goes to 0 of x times sine of 1 over x divided by x, or just sine of 1 over x. And now as x approaches 0, right, this is oscillating more and more rapidly. This limit does not exist. So in this case, we see that f is not differentiable And I'm often going to abbreviate differentiable as diffball here. So f is not differentiable at x is equal to 0. Okay, well, similarly, let's see what happens over here. So over here, if I take the limit as x goes to 0, again, of g of x minus g of 0 over x minus 0. This will be the limit as x goes to 0 of, this will be x squared sine of 1 over x minus 0 over x minus 0, which in this case, once I cancel a factor of x in the numerator and denominator, I'll end up with an x sine of 1 over x. And now this limit does exist and is equal to 0. So this actually tells me, because this limit exists, that tells me my function is differentiable. So g is differentiable at x is equal to 0. Okay. Now, from these two things, we can draw one immediate conclusion, which is that both of these functions were continuous at 0. One is differentiable, the other is not, right? So this, just from this example, right, we can see that just being continuous at a point does not imply differentiability at that point, right? This is continuous at x is equal to 0, but it is not differentiable at x is equal to 0. Okay, so we sort of get, just from this example, right, we start to see at least one thing that doesn't hold true about these. All right, well, let's look at these a little bit more deeply now. Now, 0 is sort of the hard point to deal with because we can't really apply any of our usual derivative rules at 0. The reason being, right, we have this equation that's defining our function for most of the domain, but at 0, any neighborhood I take of 0 contains 0, right? So it contains both parts where it's defined by this equation and parts where it's defined by this equation. If I pick any point other than 0, though, I can take some neighborhood of that point that doesn't contain 0. So in that case, if I want to differentiate this anywhere else, I can just use my normal derivative rules. So for this, if I wanted to just sort of express like what is the derivative of f at x, well, I could just use product and chain rule here to take this derivative. So this would be for any x that's not 0, the derivative is sine of 1 over x minus, let's see, get a minus because that derivative is going to be cosine x and x squared. So 1 over x cosine of 1 over x when x is not equal to 0. When x is equal to 0, again, we just calculated that, oh, sorry, in this case, we calculated that the derivative is not differentiable at that point. So we'll just say does not exist if x is equal to 0. All right, over here for the function g, if I wanted to do something similar, so I could say, okay, g prime of x. Let's see. Well, we calculated that to be 0 when x is equal to 0. And here, if we just use our normal sort of derivative rules, so we would get a 2x, the derivative of the first part times leave the second part alone. And then we would leave the first part alone times the derivative of the second part. With a little bit of simplification, that's just going to become a minus cosine of 1 over x. X is not 0. All right. Now, one of the things I want to observe, particularly of this, so here, our function is differentiable at every point in our domain, okay? So we would say here that g is differentiable on all of R, Okay, and here is the derivative at every point in R. Okay, but if I look at this function g prime of x, let me ask myself what happens to this function g prime as x goes to 0. Well, I can just write down g prime of x. Right, if I look at, again, I'm not concerned, I'm looking at the limits. I'm not concerned what's happening at 0. I want to know what's happening as I get close to 0. That'd be the limit of this function. Now, if I look at this, this term is going to 0, right? So x is going to 0. Sine of 1 over x is oscillating, but it's bounded. So this term is going to 0. However, this term over here is oscillating. There's nothing driving it to 0. In fact, as x is getting closer and closer to 0, it's oscillating more and more rapidly between -1 and 1. So in fact, this limit does not exist. I shouldn't write equals does not exist, right? So this limit here does not exist. And so what we notice here is that g prime is not continuous at 0. Okay. So even here, I can have a function that's differentiable at every value, and the derivative function that I get out is not continuous. Okay. Now, this might seem a little surprising at first. If you sort of think back to all the examples you saw in calculus. Well, first of all, most of the functions you looked at in calculus, many of them were continuous at every real number. Okay. So they were continuous everywhere. And their derivatives were also continuous at every real number. Okay, but now here you're seeing an example of a function g. This is continuous for every real value of x. It's continuous on all of R. Its derivative function, however, is not continuous. Okay, so this is, I think, the first example of like you have to be careful about a lot of these mental images you might have built up from thinking about functions from calculus 1 or calculus 2, because often what can actually happen, the full realm of possibility, allows much more strange things to happen. Okay. Now, it actually turns out, as we'll see momentarily, that while even if a function is differentiable, I can't guarantee that the derivative function is continuous. It turns out I can still expect some fairly nice properties. We're going to sort of preview that a little bit, and then we'll come back later and prove the details. What we want to do is sort of use these two examples now to help us generate some ideas for the types of theorems we're going to prove. Now, the first thing we're going to prove is that if a function is differentiable at a, then that same function is continuous at a. Now, be careful because you might be tempted to say, wait, didn't you just say the opposite? What I said earlier is, or what I just said before, is that if f is differentiable at a, then f prime is not necessarily continuous at a. So the derivative function may not be continuous at a, but if f is differentiable at a, then that function f must be continuous at that same point a. Okay. Let's look at a proof of that. Well, so suppose f is differentiable at x is equal to a. Now, I'm going to look at the following limit. Now, my goal is to show that f is continuous at a. So if you think about, right, what do we mean by that, right? Typically, right, if I want f to be continuous at a, then what I want is I want the limit as x approaches a of f of x to be equal to f of a. Okay. So here I'm looking at the difference. What I'm going to do is I'm going to show that the limit of this difference has to be 0, and therefore this limit has to hold. And we'll justify that at the end. But so my goal is to show that this is actually equal to 0. All right. So, excuse me. Let's write out what this is. Or sorry, let's re-express this rather. So what I'm going to do is I am going to rewrite this as f of x minus f of a over x minus a times x minus a. Now, right, notice you could simplify this to get back over here, but you might ask, sort of, why would I do this? Well, I need to somehow use my condition that f is differentiable at x is equal to a. So somehow, in order to do that, I need to take a limit of something that looks like this. So really what I'm sort of doing is saying, okay, I want to say something about this. I know something about this, so I need to introduce something of this form, and well, then I'm just going to have to pick up this sort of correction factor here. Hopefully I can deal with that. Okay. Now, looking at this expression, I know the limit as x approaches a of this, right? The limit as x approaches a of this is f prime of a, and that exists because my hypothesis is that f is differentiable at x is equal to a. I know that the limit as x approaches a of this exists. This is just a polynomial, right? It's a linear function in x, so it's continuous, right? And so I can just plug in here, x is equal to a. And so because the limit of each piece exists, I can rewrite the limit of this product as the product of the limit of each respective piece. So I can rewrite this as a limit as x approaches a of f of x minus f of a over x minus a times the limit as x approaches a of x minus a. Now, this is just f prime of a, and again, I know that exists because my hypothesis is that this function is differentiable. And I know this limit exists, and it's a polynomial, so it's continuous. The limit as x approaches a of this is just this evaluated at x is equal to a. So this will just be a minus a, which is 0. And so I get this is 0. Okay. Now again, formally I haven't shown this yet. So how do I show this? Well, then if I look at the limit as x approaches a of f of x, I can rewrite this as the limit as x approaches a of f of x minus f of a plus f of a. I know the limit of this piece exists because I just showed that limit exists and is equal to 0. I know the limit of this piece exists because f of a is just a constant, right? The limit of any constant exists. So this is then equal to the limit as x approaches a of f of x minus f of a plus the limit as x approaches a of f of a. Well, again, this is 0. I calculated that up here. This is the limit of a constant. It's just the constant. And so I've shown that the limit as x approaches a of f of x is equal to f of a, which is exactly what it means for f to be continuous at a. So again, we've seen continuity does not imply differentiability, but now what we're seeing here is that differentiability of a function at a point does imply continuity of the function at that point. Now, in practice, this doesn't maybe come in particularly handy, if your goal is to prove something is continuous and you have some expression for a function sitting in front of you, it's probably not the most helpful thing. But when we're writing proofs or doing things theoretically, what this tells us is like we can just write we don't have to write, suppose f is differentiable at a and f is continuous at a, because if it's differentiable, it's automatically continuous. So this often comes in more, it turns out to be a little more helpful, more in theoretical proofs than it is in actually, say, looking at a particular function and determining whether or not it is continuous at a given point. That it would rarely be the case that the easiest way to do it is to actually try and determine if it's differentiable to determine that it's continuous. Usually, it's just easier to examine the continuity on its own. All right. Now, the next theorem I want to talk about gets back to something I was remarking on earlier, and we're just going to sort of preview this theorem. I'm not going to say, we're certainly not going to prove it yet. We need to build some more tools first. But this is a theorem called Darboux theorem. So it says if a function is differentiable on the closed interval AB, so assume your function is differentiable at every point on some closed interval, we know, right, from the example we saw earlier, that does not mean that the derivative is continuous on that interval. It means the function f has to be continuous on this interval, but it does not mean that the derivative function is continuous on that interval. But what this says is if it is differentiable on this interval and if k is some number between f prime of a and f prime of b, then there exists a value c in ab such that f prime of c is equal to k. Now, when you're looking at this, you should be saying, wait, hold on, that looks like the intermediate value theorem. And for good reason, it is very similar. So this looks like the intermediate value theorem, but now it's applied to f prime of a. So what Darboux's theorem is saying is we already know that f being differentiable does not imply that f prime is continuous. But what this says is even though f prime may not be continuous, it still satisfies an intermediate value property. So what we'll see later on is that even though f prime isn't necessarily continuous just because f is differentiable, there's still some really nice properties of a derivative function if the derivative exists on some interval, right? So what we're going to see is that while you can't necessarily assume that derivative functions are going to be continuous, they're still going to be relatively nice, especially when just compared to the whole wide world of functions, which can have many types of varied and in many cases, in lots of cases, ugly, horrible behavior, right? Functions that are the derivative of some other function, they may not be continuous, but they also can't be quite so bad. Okay, so again, this is just a little preview of something that's to come. Okay. All right. Now, as I mentioned earlier, we're using that fundamentally that same limit definition of the derivative. You should expect that you're going to get all of the same algebra of derivative type properties. Okay. Now, this is the theorem as it is stated in the book. And I'm going to make in a minute one small correction to it. But let's first go through it. It's a very minor technical correction, but let's first go through this. So let f and g be differentiable at a point A and let c be a real number, right? Then basically we're saying if you want to take the derivative of a constant times f, you can pull the constant out and just take the derivative of the function. If you have the derivative of a sum of two functions, that's just the sum of the derivative of each function. Same with differences. And then, of course, we have these last two, which give us the product rule and quotient rule. So this says f times g prime is f prime g plus f g prime. So that's the product rule. And then f divided by g prime, right, is this expression, which is just the quotient rule, again, provided that denominator is not equal to 0. Now, a couple of remarks, right? This is sort of, each of these is giving us two things at once. So, right, for example, here in the product rule, this is telling me not only that f times g is differentiable, so if f is differentiable and g is differentiable, then f times g is differentiable. It's also giving me this formula for how to calculate the derivative. So each of these you can think of as sort of two pieces of information at once. It's simultaneously telling you that this new function is differentiable, f times g, and also it's telling you how to calculate the derivative of f times g from information about f and g individually. Okay. So none of these results should be particularly shocking. Now, here is the one sort of little technical point that I think is worth taking some time to consider. And let's do this maybe within the context of thinking about the product rule, although similar things would actually apply. All these issues I'm going to talk about pop up where you're combining two of the functions. So this says let f and g be differentiable at a. So we have to be a little bit careful about what exactly we mean by that. So consider the following sort of situation. So what if I defined f, oh, this color is not very good, this board. So what if I took a function f and I defined it from a, some set a into the reals, and I'm going to define a to be this set that I keep using for seemingly everything because it's a nice, convenient example. Okay. And I'm going to define this function by f of x is equal to x. Okay. Now, if I do this, then f is differentiable at 0, and f prime of 0 will be 1. Okay. Now let me define a function g from a set B into the reals. I'm going to define B to be the set of numbers of the form pi over n, where n is a natural number, union 0. And I'm going to define, let's say, g of x to be x squared. Okay. And if I do this, then g prime of 0 is just 0. So let's talk through each of these briefly. So here, right, when I say f is differentiable at a, right, back to my definition, I'm saying that a is an accumulation point of the domain. So 0 is an accumulation point of this set, which it is, and also 0 is in this set. Okay. Similarly, if I say g is differentiable at a, then I'm saying that that point, in this case 0, is in this set, which it is, and it's an accumulation point of this set, which it is. Okay. Now, here comes the problem. If I now want to look at the function f times g of x, this function f times g is only defined where the functions f and g are both defined. So this function f times g is only going to be defined on the intersection of these two sets. Well, the intersection of these two sets these are numbers of the form pi over n. These are numbers of the form 1 over n. These two don't intersect at all. The only point of intersection is 0. So this function f times g, the only place it's going to actually be defined is at 0. But you have a problem here because now 0 is not an accumulation point of this domain. So it doesn't make any sense to talk about the derivative of f times g, even though it makes sense to talk about the derivative of f, and it makes sense to talk about the derivative of g. It doesn't make sense here to talk about the derivative of f times g because this is no longer an accumulation point. 0 is no longer an accumulation point of the domain. Okay. So somehow we need to be a little clearer up here about exactly what conditions we want to hold. Now, primarily there are two ways to fix this. One way is actually to say your domains of f and g have to be the same. They have to be defined on some common domain and then be differentiable on that domain. So that guarantees that a is an accumulation point of both f and g, and f times g will have exactly the same domain. The other way you can do this is to write out some additional condition about guaranteeing that a is an accumulation point of the intersection of the domain of f and the domain of g. Those are both perfectly reasonable things. I consulted a few books as I was thinking about this to sort of see, well, what's the most common way? And far and away, the most common way to deal with this is to just require that f and g be differentiable on a common domain D. So that's exactly what we're going to do here. So I'm gonna so this is actually exactly how it's stated in the book. My guess is that they intended that these be defined on a common domain. But so I'll just sort of give you a corrected version, right? Where I'm just going to add in this condition here that f and g are defined on a common domain D, and they're differentiable at A, or so A is in D, and A is an accumulation point of this common domain D. Okay, then all these conditions hold with no problem. Okay, again, very minor technical point, but something to, I mean, this is a graduate analysis course. If nothing else, it's about considering things that other people might consider minor technical details, right? So it's important to take a little care in that. Now, the last thing I want to do is I want you to get, we're not going to prove all of these. Again, you may have seen proofs of some of these before, but let's at least sketch out the proof of one of them. I think the first two are straightforward enough that you don't necessarily like learn a whole lot by doing them. This one, the quotient rule becomes sort of just algebraically tedious, so that you get so frustrated at the algebra sometimes you're losing the plot. So I think the product rule one is a really nice one because it sort of straddles the two. So let's see if we can prove the product rule. Okay. So let's start. So we're going to suppose f and g defined on this common domain D into R are differentiable at x is equal to A. Okay. And now what I want to show is that the following limit exists and is equal to the sort of right thing that we should get from the product rule. Okay. So I'm going to look at this limit as x approaches A of f times g of x minus f times g of A all over x minus A, right? So this is just this limit definition of the derivative. And now I'm looking at the derivative of the function f times g. Okay, well, what is the function f times g? The function f times g is just the function. So the function f times g of x is just the function that returns f of x times g of x. Okay, and f times g of A will be f of A times g of A. Now, remember here my hypothesis here, right, is that f and g are differentiable. So somehow I need to get something in here that looks like the derivative of f and or the derivative of g. Okay. Now the problem I have right now, like the x value in the f function is changing from x to a, and at the same time the x value in the g function is changing from x to a. And what I'd like to do is sort of break that down, sort of into f changes its input from x to a, and then g changes its input. And so the way I'm going to do that is I'm going to add and subtract a term here. So right in the middle here, I am going to go ahead and add in, well, I'm going to add in subtract. So I'm going to subtract first. F of a times g of x. Should get an f of a g of a. Okay. So now what I want you to notice here, first of all, right, if I were to look at these two terms would sum to zero and I'd get back to here. So these two expressions really are equal. Okay. But now if I group these terms and these terms, so now notice here in these two terms, g of x is fixed. F of x is changing from f of x to f of a. Over here, f of a is fixed, and g of x is changing from g of x to g of a. And in fact, because I'm doing that, I could actually, from these two terms, I could factor out a g of x. And from these two terms, I could factor out an f of a. So doing a little bit of algebra here, and you may want to break this up if you haven't seen or thought about this in a while. I'm going to sort of skip a few algebraic steps. I'm not doing any calculus or any analysis here. This is just some algebra to rewrite all of this. I could rewrite this as g of x. So this whole expression could become g of x times f of x minus f of a over x minus a plus f of a times g of x minus g of a over x minus a. Okay. So essentially, I've got a sum here. I'm going to break it up into this piece over the denominator plus this piece over the denominator. And then I'm going to factor out a g of x here and factor out an f of a here. Okay, that's how I end up there. All right. So now what can I do? So if I look at these, the first thing I sort of think, okay, I've got a limit. I might like to sort of break it up into the limit of each piece. Well, I've got a sum here. So I could say the limit of the sum is the sum of the limits if I know that each of these individual limits exist. Okay. Well, in order to know this limit exists, I would probably want to say, well, this is the limit of a product. Let me look at the limit of each piece. Okay. Well, so let's do that. Let's sort of think of this in four chunks, right? So there's one chunk, two chunks, three chunks, four chunks. And let's ask ourselves, does the limit as x approaches a of each of these pieces exist? Now, these two, if I just look at these two, the limit as x approaches a of this exists because f is differentiable at a. This is just f prime of a. Likewise, this limit exists because g is differentiable at a. This is just g prime of a. The limit of this piece exists because it's just a constant, right? The limit of any constant is just that constant. So this is just f of a. Now, the limit as x approaches a of this piece, requires a little more thought. So this is actually going to be just about g. Well, what do I know? I know g is differentiable at x is equal to a, and we just proved that if g is differentiable at a, then it has to be continuous at a. So since this is continuous at a, the limit as x approaches a of g of x must exist, and it must be g of a. So now what I can do is I can break all of this up, right, into limit as x approaches a of g of x times the limit as x approaches a of f of x minus f of a over x minus a plus the limit as x approaches a of f of a times the limit as x approaches a of g of x minus g of a over x minus a. Okay. And now, well, we've already gone through precisely what each of these pieces is, right? So this first piece, because g is continuous, it's differentiable, which implies it's continuous. Therefore, this is just g of a. This piece is just f prime of a. This piece is a constant, so it's just f of a. And this piece is g prime of a. And now this is almost exactly, if I just use the fact that multiplication is commutative here, then I now have that this limit exists and is equal to this. Now that I know this limit exists, I know that this is just the derivative. I can now say the derivative of this function exists at A, and it's equal to this. Okay. So I can prove the product rule here. And in fact, most of these work sort of in a similar way. You write down, if you wanted to do f plus g, okay, you write down what the limit expression for the derivative would have to be. You do some things until you can break it up into pieces that have derivative of f and derivative of g. You come up with that expression, and then you go, oh, okay, that limit must exist. Therefore, the derivative of that sum function existed and will be equal to this other thing. Okay. The difficulties really only come in how you algebraically deal with these things. And again, the quotient rule one, it can be really nasty. Again, just the algebra is nasty though. It's like conceptually, we've covered all of the same topics you would need to cover. It's just you're going to have to do some really clever algebraic manipulations to get the answer you want. So we will stop there for this video. In the next video, we're going to look at a few other properties that follow from the definition of the derivative. So in particular, you'll notice the one derivative rule we didn't discuss today is the chain rule. So we'll spend a little time talking about the chain rule. And then we'll start to look at like an inverse function theorem that tells us some things about how the derivative of a function and the derivative of its inverse are related to one another. And on its own, this won't be, as we're going to state it, it won't be the most, you won't look at it and go, oh, I can clearly see that this is a really important theorem. But what we'll see is that the results we get are actually quite useful in a lot of other things we want to prove. So there'll be really useful results to have on hand once we start pushing into talking more about the mean value theorem and some of the consequences of the mean value theorem and Fermat's theorem. So we will stop there for this video, and next time push forward into some more properties of derivatives.